This is about solving equations of different kinds. And the best way to get good at it is to practice. So that's how we're going to start with practicing because, um, so let's start with one example. X to the 4 minus 25 x squared plus 144 equal to 0. Now, this is not a quadratic equation as is because the degree of this polynomial is 4. A quadratic equation has degree 2. However, we notice that the two terms which contain the variable, one is the square of the other. X squared squared is going to give us x to the 4. So this is in reality quadratic-like equation. We need to change the variable. So pretend this is a new variable, and you can label it anything you want. Let's say u. Okay, so pretend this guy is u. If this was u, then this term would be negative 25 u, not u squared, the entire thing. So assume, this is why I left some space down here. Okay, so assume u is equal to x squared. So we replace x squared with u because we're assuming they're the same. And then as a consequence of that, u squared would be x to the, well, let's see, we're going to square this guy. And remember, squaring means that we're going to multiply the exponents. So this is going to be, I was going to put 3, but of course that would be wrong. It has to be 4. There we go, 4. So x to the 4 should be replaced with u cubed, rather with u squared. So u squared minus 25u plus 144 equals 0. So this equation can be rewritten in this form, which is a quadratic equation. Now the variable is not the same, but that's okay. We're going to take care of the variable after we solve this equation. Okay, this equation is doable. It is a quadratic. We definitely know how to solve quadratic equations. We can attempt to do this by let me think how we can do this. Factoring could work, will work, should work, but we don't know. There's many numbers that multiply to 144. There is 72 and 2, and then there is 4 and another number and 3. There are many numbers that multiply to 144. So maybe that's, factoring is going to be a little bit lengthy. I guess we can use the quadratic formula. So u would be the opposite of negative 25, which would be just the 25, plus or minus square root. 25 squared is 625, if I'm not mistaken. And then we subtract 4 times AC. So we need to figure out 4 times 144. 144 times 4 is 576. 576. And then we divide by 2. So 25 plus or minus square root of 625 minus 576. So minus 625 equals, and of course I did the subtraction backwards. On the calculator, I did this minus that instead of this minus this, and that's why on the calculator it shows a negative, but we know it should be positive because we're subtracting the big number minus the smaller of the two. So we end up with 49 divided by 2, and that is actually 7. 25 plus or minus 7 divided by 2, and that means there are two possibilities. 25 plus 7 is 32. Divided by 2 is 16. So u could be 16, or 25 minus 7 is 18. Divided by 2 is 9. U equals 9. Okay, but don't finish here. That's what U is, but the original problem had X, not U in it. Now U is X squared. So what this is telling us is that X squared is 16 and X squared is 9. And consequently, when we take the square root on each one of those two cases, we end up with X equals plus or minus 4 and X equals plus or minus 3. So we have 4 solutions. How many solutions? 4 solutions. Sometimes we will ask students to write a solution set. So we just put down all the elements. So going from smallest to largest, we have -4, -3, 3, and 4. So that is even more clear that we have 4 different solutions to this equation. Let's do more examples. 2. X cubed minus 3x squared minus 4x plus 12 equal to 0. Now, this polynomial is not a quadratic-like equation. In a quadratic-like equation, we have typically, well, two terms, where one of the variables is the other one squared. Well, the whole thing, I'm thinking of the whole thing, one of the parts is present and the other part is the square of that. So there are two, no more x's, just two, and one is the square of the other. Okay, here we got 3, 1, 2, 3. So right off the top, this does not qualify. Well, there's actually 4 plus the constant term. As is, because there are 4 terms, yeah, this does not qualify as a quadratic. All right, but the other thing we could do with this is perhaps a factor 2 by 2. And sometimes factoring 2 by 2 can help solve the equation. All right, so what can we factor from those two terms? Well, of course, x squared, and we have x minus 3. And then anticipating we want to end up with x minus 3, we want to change that into a negative. And the way we do that is by factoring the negative. So factor the negative 4. -4, factor it out, and we end up with x minus 3 again. Now the reason, the way we can check that we did this correctly is by thinking, if we multiply this back, you know, -4 times x is -4x. -4 times -3 is positive 12. So if we multiply back and we obtain what we already had, then we're good. Okay, notice that this factor is the same. X minus 3 and x minus 3 is the same on the two terms. We have two big terms. This that I'm pointing to is a term. This is another term, and we are subtracting the 2. Okay, they have something in common, x minus 3 and x minus 3, just like those two had something in common. What do they have in common? X squared, so that got factored out. Those two have something in common, 4, so that got factored out. Those two have something in common, x minus 3, so that gets to be factored out. And what is left over is x squared minus 4. Okay. And then we know this can be factored even farther. This is going to be, that is a difference of squares, x minus 2 and x plus 2. All right. So now we used what I call the zero product property, which states that if a product is equal to 0, then each one of the factors could be 0. And that is the only thing that could happen. There's nothing else that could cause this product to be 0. I was checking that I was actually taping this because yesterday I was taping a lesson. I forget about which one. I wanted to forget it quickly because, and um, and I had not pressed the record button, so I was talking to myself for a while. That wasn't very. I mean, it's funny after the fact, but it wasn't funny when I was doing it. Anyway, so the zero product property says that the only way we can get 0 is if at least one of those is equal to 0. So we have different possibilities. X minus 3 could be 0, or x minus 2 is equal to 0, or x plus 2 is equal to 0. And each one of those yields a different solution. So on one hand, we have 3, or 2, or negative 2. So those are our solutions. Again, we may ask students to write down a solution set, which in this case, and typically we write them from smallest to largest. So the smallest one is negative 2, 2, 3, and there we go. Please avoid using plus minus in this case when we are writing a solution set. Example 3. I'm going to start it here and then continue on the next page because we're not going to have enough room to write down example 3 completely on this page. Okay, this one is weird. X minus 10x to the 1/2 plus 21 equal to 0. Okay, so we notice that we have 3 terms. So right off the top, we're thinking maybe this is quadratic. We got 2 terms that have a variable, and this term has the square of that. Because if we square x to the 1/2, then we end up with x. Okay, so we can let, instead of writing assume, we can write down let u be x to the 1/2. So u squared would be, now let's do this step by step. X to the 1/2 squared, and you know when we have an exponent on top of another exponent in this fashion, we multiply the exponents, so we end up with 2 over 2, which is the same thing as x to the 1. And when we have an exponent of 1, we don't write it down. So there, this is the square of u, if this is u. If this is u, when we square it, we end up with this. So now we can rewrite our equation as u squared. So the x takes the place of the u squared, minus 10. X to the 1/2 is u, plus 21 equal to 0. Okay. And then we have to do more. We can factor this. I'm thinking we should be able to, but let's see. We don't know until we know. If we put 7 and 3, let's see, we have a positive, so we need both of those to be negative. Yep, and that adds up to negative 10, so we're good. So again, we're using the 0, whoops, I missed the 0 part, product property, which states that if the only way we can multiply to 0 is if at least one of the factors is equal to 0. So we have u minus 7 equaling 0, u minus 3 equaling 0, and so u equals 7, u equals 3. And sometimes students get so excited to get to this point, they box it, and then they walk away without realizing, wait a minute, the original problem had x's in it. So we really want to know um, we want to know the x value, not the u value. We made up the u value. Now u is equal to x to the 1/2. So that means that x to the 1/2 is equal to 7, and x to the 1/2 is equal to 3. So that means the square root of x is 7. What should x be? Now think about that. Square root of x is 7. Or the other way to say it is the square root of what number gives us 7? Well, that number has to be 49. And the other number has to be 9. So there's our two solutions, 9 and 49. Very tricky. We really want to practice this. Um, this is a skill that we develop by practicing. 4. Example 4. X cubed minus 7x squared plus 16x minus 112 equal to 0. Okay, this has 4 terms. It looks like we should factor it out by grouping um, because it doesn't have 3 terms. That doesn't mean that it cannot be uh, factored if you have 3 terms, but this is kind of a giveaway. If you have 4 terms, not all the time, but it is likely that we can factor by grouping. So I'm going to group those two. What do they have in common? X squared. So we're going to factor out x squared, and then what is left over is x minus 7 plus, I'm going to guess 16 goes into 112. If not, then it doesn't, but let's check. So 112 divide by 16 and see if it goes into it. Sure enough, and it is 7. So we can factor out 16, x minus, well, 12 is 16 times 7. So when the 16 gets pulled out of the 12, we still have 7. Okay, so we started out with 4 terms. Terms are things that we add or subtract together. 1, 2, 3, 4. And now we end up with 2 terms. That can be a little confusing. But think of this as one term and this another term. Now, within themselves, there is terms. Yeah, so it gets a little complicated because there's a hierarchy of terms and factors and so forth. But we think of this as one term, one big term, because we're not, I mean, think of this as a quantity. X minus 7 is just a quantity in parentheses. Multiplied with another one, that means that we are not really adding or subtracting. Now, within this quantity, sure, we are subtracting. But think of it as a quantity as a whole, times this one. So we're not really adding or subtracting anything here. Same thing, 16 times whatever that is. Okay. Now, what do they have in common? X minus 7. So we may factor that out. So we have x minus 7 quantity x squared plus 16 equal to 0. Okay. I cannot think of factoring this immediately because this is not a difference of squares. We know how to factor difference of squares. This is an addition of squares. It factors similarly if we were to factor it, but instead I'm just going to use the zero product property. Zero product property. Okay, so on one hand, x minus 7 is equal to 0. On the other hand, x squared plus 16 is equal to 0. From here, 7 is one of the solutions. In this case, what we're going to do is I'm going to write this next to it. X squared equals, I'm going to subtract 16 from both sides of the equation. And that means that if we take the square root on both sides, we're going to end up with x equaling square root of 16 is 4. But then we have to use complex numbers because we cannot have the square root of a negative number if x is positive. Rather, if we're, yeah, if x is a real number, rather. If x is a real number, we cannot square and expect to have a negative output. So we have to use complex numbers. The square root of -1 is I, and there are two possibilities, plus or minus. So the solution set, I'm trying to squeeze it here. Let's just write down the set, contains the 7, 4i, and -4i. So this is our solution set. I'm just going to write it here. Solution set, and I'm going to put an arrow there, showing that this is the solution set. That was example 4. Example 5. Whoops, I wasn't looking. 5, there we go. Oh, this is an interesting one. 6x cubed, 6x cubed minus 5x to the 3 halves minus 4 equal to 0. Whoa. Okay, so I noticed that there's 3 terms. So that tells me maybe this is a quadratic-like equation. This is, the exponent is twice as much as this one, and that's kind of what you want to look at it at. If the exponent is twice as much, this is twice as much as that. Or the other way to think of it is this is half that exponent. In all the problems we've done where we use substitution, yeah, here we did that. You know, this exponent is twice as much as that in example 1. In our example 2, no, we did not use that. In example 3, the exponent here is 1, and this is a half. So this is half of that exponent. In example 4, nope, we did not do that. In example 5, notice that this exponent is twice as this one, or this one is half of that one, either way. And then there is no more excess to worry about, or more variables. So that means this is a quadratic-like equation. So we're going to let u be x with a smaller one. Because we already checked that this is half of that as an exponent, u squared will be x cubed, you know, because we're going to square this. So that means we're going to have a 2 multiplying with the 3 halves. The 2 times 3 halves is 3, which matches that. So our equation becomes 6u squared. That's weird because the 3 became a 2, minus 5u minus 4 equal to 0. Okay, and now we're going to solve this second equation, which is not the original equation. Let's think about this. I'm trying to factor. Let's see. If we were to factor, I'm going to try 6u and u. And then if we have 2 and 2, nope, that doesn't seem to work. So I'm playing the guessing game, and that's okay. Because there are only so many guesses to go through. A lot of people downplay the guessing, but guessing is a good thing. It's not necessarily a bad thing, especially when the number of possibilities is reduced in a significant way. You know, if you're guessing 100 numbers, then that's too much. But if you're guessing among, 4 or 5 choices, that's not bad. That's actually okay. Anyway, how about 4 and 6? So if we put a 4 here and 6, that's 24. No, that won't work. So by inspection, by looking at this and trying a few things in my head, I realized this combination is probably not going to work. You're probably thinking, I knew that. Why didn't you use this one? Well, because I have a systematic way of going. I start with the biggest number here, and then I go down to the next one. How about 4 and 1? Let me put a 4. Yeah, 4 and 1 and see if that works. So that is 3 and 8. Oh, that seems promising. If we put a negative here, then we have a negative 8 because I'm looking at the 5 and a positive 1. Yep, that works. All right. Now, if this had not worked, we would have to go to either completing the square or the quadratic formula. But we were lucky enough to make this work. Okay, so we use the zero product property and realize, well, 3u minus 4 is 0, 2u plus 1, 0. Those are the possibilities. So I'm going to do 2 steps in one. I hope that is okay. Add the 4 to both sides of the equation, and then divide by 3. I'm going to do the same thing here. We're going to move the 1 to the other side of the equation, and then divide by 2. Okay. But u is x to the 3 halves. Huh. Okay. So x to the 3 halves is equal to 4/3. Boy, that's complicated. X to the 3 halves equals negative 1/2. Because now we have to figure this out. So that means that if we square both sides, that gets a little tricky. If we square both sides, we end up with x cubed, but then we have to square this, and that's going to give us 16 over 9. And if we square this guy, yeah, that's a tricky one. X cubed will be, I'm thinking because when we square, we lose the negative. But if we were to cube root it first, let's finish this up and then go from there. So this is 1/4 when we square. So again, the reason why we want to go from here to here is because when we square, when we square both sides of the equation, then when we multiply the exponents, we end up with x cubed. All right, and then the last part is easy. Once taking the cube root is easy. So x would have to be the cube root of 16 over 9. Man, we have to simplify this because 16 is really 2 to the 4, or let me write it differently. So first, let's write this down: cube root of 16 over cube root of 9, and then we can split 16 into 8 times 2. And the reason why we want to do that is because 8 has a perfect cube root. So this would end up being 2. I don't want to rush here. Let me continue on the next page. So I'm still continuing this equation down here. We can split this into the cube root of 8 times the cube root of 2 over the cube root of 9. And that is 2, because the cube root of 8 is 2, cube root of 2 over cube root of 9. So that is one solution. Whoa, a positive solution. The other solution comes from taking the cube root of this, but that is easier. It's not as complicated. And x is going to be the cube root of 1 over 4, which is just the cube root of 1 over the cube root of 4, and that is, of course, 1 over the cube root of 4, which is a positive number. I'm looking back at the original equation. Yeah, we can take the square root and cube it, so we are good. So the solution set for this equation contains two elements, 1 over the cube root of 4 and 2 cube root of 2 over cube root of 9. If we rationalize that, it should be okay, but if I tend not to rationalize things, but that depends on the instructor. Some instructors want it, some instructors don't. Yeah, that you really want to ask instructors whether they prefer solutions without roots in the denominator or not. That was a doozy. That was a big one. Example 6. 6x cubed minus 5x squared minus 4x equal to 0. Whoa, we got a lot of x's. That's the first thing that pops to us. There's tons of x's. Right off the top, we should factor that out, x. So we end up with 6x squared minus 5x minus 4. If we see too many x's across the board in every one of the terms, factor that out if we're solving an equation. Yeah. Don't divide by x, because if we divide by x, we would be losing a solution. So don't divide by x. Instead, we're going to factor this. So we have x. This looks familiar. 6, negative 5, negative 4. 6, negative 5, negative 4 in a quadratic. We did this work already. 3 and negative 4, 2 and 1. 3, negative 4, 2, and 1. Let's double check. 6, 8, negative, plus 3, negative 5, and then negative 4. Yep, that works out. So we're going to apply the zero product property, which states that if the only way a product can be 0 is if at least one of those three factors is equal to 0. So either x is 0, or 3x minus 4 is 0, or 2x plus 1 is 0. Well, here we already got a solution. Another possible solution would be x, and I'm going to do two steps at once. Add the 4 to then divide by 3. Subtract the 1 to then divide by 2. So we have 3 solutions. Another example, 7. Let me make sure my numbers are correct. That was example 6, yep. So example 7. Whoa, this is a big example. Let's see. 30x cubed plus 599x squared, boy, minus 20x equal to 0. Well, in addition of the big gigantic numbers, what I notice is that there is many x's, x, 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 factor out the x, just as in the last example. So we got 30x squared plus 599x minus 20 equal to 0. Factoring this will not be obvious or trivial. I almost want to, because if we use the quadratic formula, well, this number is gigantic, 599. Now let's think about this. So we need two numbers. Let's see if we can at least start factoring things out. We need two numbers that multiply to 30. Okay, so we got several possibilities. Let's write down some of the possibilities, like 15 and 2. That could work. 15x and 2x. And we can have 10x and 3x. That's another possibility. Or we can have 6x and 5x. I'm missing 1, 30x, and just 1x. We don't put down the 1, but I'm emphasizing that it is 1. And then if we start all over, I mean, if we continue, we're going to have 5x here and 6x also. That's another possibility. But that's the same thing. Since we already have 6x and 5x as one of the possibilities, this possibility is the same as just flipping those two. Okay. For the 20, okay, there's, again, different possibilities. We have 1 and 20, or 2 and 10, or 4 and 5. Those are the pairs that make up the 20, or 5 and 4. And you're probably thinking, wait a minute, we already did 4 and 5, so why are you doing 5 and 4? Well, this is the reason. We want to have all the possible combinations, possible ways to combine things together, such as with 6 and 4, and maybe 5 and 5. Yes. But if we switch those two around, and we also switch those two around, we're not gaining anything. Yeah, double switching doesn't gain anything. So in order to avoid the double switching, one of our lists, either this one or that one, has to include the switch, but the other list would not include the switch. So for instance, here, we don't include the switch, but this one should. Otherwise, we're going to be double switching. So let's continue our list. 1, 2, 4, 5, and then we can have 10 and 2 and 20 and 1. Fortunately, there aren't too many on this side. Okay, now we want this to be to get up to 599 by foiling. So the outer terms and the inner terms have to get all the way up to 599. 15 and 20, well, that's about 300. Actually, that is exactly 300. That's all about half of that. Plus or minus 2, that doesn't work. 100, I'm doing the foiling in my head. 106, nope, that doesn't reach 500. 30, and well, actually, I don't have to go in order. I have to kind of check all. Whoa, there's a lot of combinations. 1, 2, 3, 4 of those. 1, 2, 3, 4, 5, 6. There's actually 24 ways to combine outer terms with inner terms. But we want a big number. That's kind of a little bit of a bigger way. We want a big number. So that's not going to work. 10 and 10. What about a combination? 15 and 20. Oh, I know what. Since we want a big number, why don't we pick the biggest number here and the biggest number in this list? 30 and 20, 600. Whoa. Whoa, that seems to be close. Let's attempt that. So if we do 30x which will force us to have an x by itself. And then if we put 20 here, all right, 20 and 30 is 600. But we want to end up, so that should be positive, with 599, but that's easily solved because we can just subtract 1. Now, by the way, there is many ways to factor things out. There's the box method and all other methods like that. Whatever works, as long as it is a legitimate way of factoring, that we are good. Now, you're probably thinking, that took too long to get this factoring. Why didn't you just use the quadratic formula? Sure, we could have. I was afraid, to be perfectly honest, to use the quadratic formula because the quadratic formula calls for squaring b. And squaring 599 is going to be a big number. I didn't want to do that. And then we're going to have also a and c. These are big numbers. So I wanted to avoid that. But that doesn't mean it wouldn't work. The quadratic formula would work. Anyway, let's move on. So we have this, and now we can use the zero product property. So either x is 0 or 30x minus 1 is 0 or x plus 20 is 0. So we have 3 solutions. I'm just going to copy this again. Or x equals 1 over 30. Remember, we add 1, divide by 30. Or negative 20. And there it is. So these are good examples to view about solving equations, the big equations, by grouping, and solving quadratic-like equations. So they're not quadratic equations the way they sit, but by some substitution, they become quadratic. And we will stop the video here.